Okay, all right. Well, glad that situation is resolved, and we'll begin now. Okay, so I guess first things first. First, I hope you guys are doing well. I've decided to just scratch Lab 5, so no Lab 5. I'll give everyone full credit for that lab. Instead, I'm assigning you a reading assignment. Okay, this is a journal article. Now it's now 2 years old. Well, October 2020, but I don't know. Do you remember at the early in the pandemic, people were trying different drugs, and one drug that was kind of suggested as a possible treatment for COVID-19 was hydroxychloroquine. I don't know if you remember this. And so, anyway, they did a medical study, and they looked into the effectiveness of hydroxychloroquine as a potential treatment for COVID-19. And so anyway, I want you to read through this article and read through kind of their design methods and how they selected participants and things of that nature. And then you can. My hope is that you can read through the statistical analysis section of the article, and that it will make sense that when they discuss p-values and confidence intervals and things like that, it will make sense. I'm also not assigning, I should say. I also have a list of questions related to the article, and I want you to kind of go through some of these questions and try to answer them. Canvas is taking its time loading them, but anyway, so again, there's nothing to turn in for this lab. You're not going to be submitting anything, but what I will do is I will draw a few of these questions, a couple questions from this I guess PDF here that I've posted, and I'll put a couple of them on the final exam. Okay, so a couple questions related to the journal article, and some of these questions that appear here will be on the final. Okay, and that's that. So this week you'll have one more kind of quiz to take this weekend, and you got kind of one last homework, and then next week. So this week we'll wrap up Chapter 8, and we'll start Chapter 9, and then next week we'll wrap up Chapter 9. There's just kind of like one more section in Chapter 9 that we'll cover on Monday, and then we'll spend the rest of Monday, I guess, doing some review, and then you'll have your final exam on Wednesday of next week. So we're really like 10 days till the end of the class, and so I don't know. It always feels these last couple of weeks always feels like they go by super quick. So I don't know. Any questions about anything? All right. I think also course evaluations will open up this week or something like that, and so if you can do me a favor and fill those out, that is always much appreciated. I do read all of your comments and feedback, and I take that into account as I kind of refine and just do little tweaks to the class. All right, well, let's go over today's content. And so I wanted to get more into hypothesis tests and a lot of the concepts, do kind of a deep dive on kind of some of the conceptual ideas of a hypothesis test. So last week on Wednesday, we introduced the hypothesis test, and we said, this is how you can test to see if the proportion in your data, contradicts the proportion that you've proposed in your hypothesis, right? And we said, the null hypothesis always starts off making some kind of claim about the population. It's, we have a question and we turn it into a testable hypothesis. And in order for it to be testable, it has to be an exact statement. It has to be a statement, and in particular, our statement is that the population has some exact proportion, right? Or I think one of the examples was that the proportion of seniors in LA County is exactly 0.202. That was one of the null hypotheses. Another null hypothesis was, the proportion of, I don't remember exactly what the examples were, but the proportion, that the coin lands heads is exactly 0.5. These are the kind of the null hypothesis statements. We're saying that the unknown population proportion P is equal to some exact value, and we call that thing P0. And we take that hypothesis and we test it against our data, right? Our data probably, when we look at our data, has a proportion that's a little bit different, right? Proportion that's a little bit different from P0. And we want to know, okay, there's a difference between P hat and P0. And is that difference significant, or is it not that big of a deal? And in particular, we want to find out, calculate this thing called the p-value. We want to know what's the probability of just getting this other value, this p hat that we got in our data. What's the probability of getting that by random chance, right? If you have a coin that's fair and it's supposed to land heads 50% of the time, what's the probability that it lands heads 60% of the time? Because that's what happened in our data. We flipped it a bunch of times and the coin landed heads 60% of the time. What's the probability that happens? Okay, or if the proportion of seniors in LA County is still exactly 20.2%, what's the probability that you take a random sample and you end up getting 24% seniors? Could that happen just by random chance, or is it evidence that, yeah, the proportion has changed? The proportion's something other than 20%. Maybe it's something a little bit higher, and that's why I'm getting 24%. Or maybe something's wrong with my coin, and that's why I'm getting 60% heads. And, we do our calculations, and either our p-value could end up being large, or our p-value could end up being small. If the p-value is less than our significance level, we say, there's a low probability this kind of data would happen by random chance. Okay? And on the other hand, if the p-value is large, we say, there's a large probability, right? So the small p-value, it means our test statistic, whatever we got in our data, is said to be extreme or highly unusual if we assume the null hypothesis is true. And therefore, the fact that this is actually our data, that this actually happened, indicates to us that this null hypothesis is wrong, right? Because the null hypothesis says, hey, if the null hypothesis were true, this kind of data shouldn't be happening. But then it happened, right? So if it happens, it's an indicator to us that the null hypothesis is wrong. So if we end up with a small p-value, our decision is going to be to reject the null hypothesis. Now, is it possible? Yes, it is technically possible that the null hypothesis is really true and that we happen to get this unusual result just by random chance. Okay? It is possible that you have a fair coin and just by random chance you flipped the coin 10 times and it landed heads all 10 times. That could happen by random chance. What's the probability that it happens that way? It's pretty darn small. So if the coin does land heads 10 times out of 10, our conclusion is going to be, something's wrong with the coin. That's why it's landing heads, all of that, okay? And we're willing to make that statement because the other side, that is the idea that the coin is actually fair and I just got really, really, really lucky, while it's not impossible, it's pretty small. The probability of the coin landing heads, 10 times out of 10 is like 1 in 1,000. And so I'm going to just say, you know what, it's small enough. I'm comfortable just ignoring it. I don't think I was one of the 1 in 1,000. I'm going to conclude the reason why I'm getting 10 heads out of 10 flips is something's wrong with my coin, that it's not a fair coin. Okay. And then on the flip side, if you end up with a large p-value, it means, your observed data could easily be produced just by randomness while the null hypothesis were true. So even if your observed data does not match the null hypothesis exactly, we wouldn't consider it to be that unusual of an outcome, right? So for example, if you flip the coin 3 times and it lands heads 3 times in a row, you'd go, that's interesting. But you wouldn't immediately conclude this has to be a fake coin, right? If you could flip the coin 3 times and it lands heads 3 times in a row, you might go, oh, that's interesting, okay? You wouldn't say, oh, something is wrong with this coin. It's got to be a trick coin. That's why I got 3 heads in a row. Because you can get 3 heads in a row with a regular coin, and that's going to happen with a 1 in 8 chance, right? So 1 in 8 isn't small enough for us to say definitely this is some sorcery happening, that something is going on with the coin. We're going to say, okay, 1 in 8, it's interesting, but it's not enough for me to come to the conclusion that my coin has been tampered with, right? We'd probably want to say, all right, I want to flip it some more, but that just might not be a possibility either, okay? So if you end up with a large p-value, your decision will be not to reject the null hypothesis. Your decision is not to reject the null hypothesis. Okay? It doesn't necessarily mean that the null hypothesis is true. We wouldn't say we accept the null hypothesis. It's just, it's not enough data for us to reject the null hypothesis. Okay, so again, looking at the coin flip example, our null hypothesis will be the coin is fair and lands heads with probability 0.5. Our alternative is that we've got some kind of strange coin, okay? And we're going to say that the probability that it lands heads is different from 0.5. That's going to be the alternative. So n is 20. If the null hypothesis were true, we would expect to get 10 heads out of 20 flips, right? If we flip the coin 20 times and we have a fair coin, we're expecting 10 heads out of 20 flips, okay? So we're going to say p is 0.5. That's what we're expecting. That goes in the middle. And our standard error is going to be 0.1118, okay? P times 1 minus p over n. Take the square root of that, n being 20. So we'll just see, what happens. So if we get exactly 10 heads out of 10 flips, then our p-value here is going to be 100%, okay? I'm getting exactly what I expected if the null hypothesis were true. And so when we calculate our p-value is what's the probability of getting your test statistic or something more unusual? Well, everything is more unusual because I'm getting exactly what I'm expecting, right? So anything different from what I expected is unusual. And if I got exactly what I'm expecting, then everything else is going to be more unusual. So I'm going to get a p-value of 1. 100% probability of either getting this data or something more unusual because I was expecting 10 heads and I got 10 heads, okay? And so here my p-hat is 0.5. My z-score is 0 because my p-hat is equal to p. And then I would look up, the area in my my tail, z, and I would kind of double it, okay? And so here I'm kind of drawing a line at 0. I'm shading everything to the right of 0. I'm shading everything to the left of 0. 100% of the area is shaded, okay? Between kind of purple is lower and more extreme. Green is higher and more extreme. All right. So what do we get if we get 9 flips? 9 flips out of 20 flips, right? So 9 heads out of 20 flips. What's the probability of getting 9 heads out of 20 flips, or something more unusual? Again, this is just an approximation. The normal distribution is just an approximation. The real number is actually going to be even a little bit higher. But 9 heads out of 20 flips is 45%. 9 divided by 20 is 45%. So how different is 45% from 50%? Well, 5 percentage points. I divide by my standard error. I get a z-score of negative 0.447. I find what's the area to the left of that, and I double it. Okay, and so the idea here is, we're expecting 10 heads out of 20 flips. We're getting 9. Okay, so that's going to be this line on the left. And I say, okay, what's the probability of getting 9 or something more unusual? So 9, 8, 7, 6, 5, 4. Or on the other side would be kind of 11 or higher. And we see, there's a high probability. That total probability is around 65%. So again, if you flip the coin 20 times and you get 9 heads, you're not immediately going to conclude, oh, something's wrong with my coin. It's biased to land heads, less often than 50%. Okay. What about if I flip the coin 20 times and I get 7 heads, right? So I get 7 heads, 13 tails. Is this unusual? Okay. And we do our calculations, and we get a z-score of negative 1.34. We do our calculations. It happens around with 18% probability. So you flip the coin 20 times, you get 7 heads, 13 tails. You go, oh, that's a little bit less than what I expected. I expected around 10 heads. I only got 7. Okay. Well, that difference is around getting 7 out of 20 flips just by random chance. So a fair coin could land heads only 7 times, or something more unusual, with 18% probability. So this is kind of what our diagram looks like here. So again, we're expecting 10 heads out of 20 flips. We're only getting 7 heads, so 7 or more unusual is to the left. The other side would be 13 or more. 13 or more. And so how often does something like that happen? Our calculations say something around 18%. Happens around 18% of the time. Okay, so not unusual enough for us to conclude that our coin is, biased. Okay. All right. Now we're starting to get into kind of the territory where maybe we come to the conclusion that something's wrong with a coin. So if I flip the coin 20 times and it lands heads only 6 times out of 20, okay, we can do our calculations, and we would get 6 or something more unusual around, 7% of the time. Okay, so it could happen, but it's not very common. Okay, it could happen, but it's not very common. And so this our conclusion depends on the significance level, right? If our significance level is 5%, this number, 7%, is a little bit higher. So it's unusual, but it's not unusual enough for me to say something's wrong with my coin. Okay. On the other hand, someone else might be a little bit, more sensitive to this, and they might have a significance level of 10%. And okay, you do the calculations, you get a p-value of 7%, and you say, well, 7% is less than 10%, and therefore I'm going to reject the null hypothesis. Okay, so this is where, depending on, how much data you feel like is necessary to make a conclusion, you look at this and you can ask, could this result have been the result of random chance? And the answer is, it could have been the result of random chance. What's the probability of getting this result by random chance alone? And it's around 7%. And you go, oh, is that high or low? And it's a bit of a judgment call. Okay, our diagram looks something like this. So if you flip the coin 20 times, if you flip a fair coin 20 times, it is possible to get only 6 heads out of 20 by random chance, but the probability of getting 6 or something more unusual, so that's 6 or something fewer, or 14 or something more greater, the probability of that happening by random chance is only around 7%. And taking it even more extreme would be if you flip the coin 20 times and you get heads only 5 times, right? 5 heads, 15 tails, or the kind of the reverse, 15 heads and 5 tails, okay? So 5 or fewer, or 15 or more. Could that happen by randomness? It could. What's the probability it happens by randomness? Only 2.5%. Only 2.5%, so around 1 in 40. So it is possible that you were just one of the 40 where you flipped a coin 20 times and you got 5 heads or fewer, okay? But because that probability is pretty small, we're going to kind of come to the conclusion and say, you know what, I feel like I wasn't just unlucky, but rather something's wrong with my coin, that it's not a fair coin, and that's why I'm getting only 5 heads out of 20, okay? For me, it's easier to believe that something's wrong with my coin rather than to believe that I was just one of these lucky 1 in 40 people who just got a unusual coin flip outcome. All right, and of course, it depends on the scenario, right? If you saw where this coin came from, right? Like you saw it being manufactured at the mint and they gave it to you, now you have a really strong belief that this coin is a fair coin. And if you do get only 5 heads out of 20 flips, you'd say, wow, that's quite bizarre, right? On the other hand, if you suspect somebody might maybe tampered with the coin to begin with, and you flip the coin 20 times and you only get 5 heads out of 20, you'd say, yeah, this really confirms it, that something's wrong with my coin. So there's kind of, a sense of, I guess, what you believe could play a role into this. But the idea here is just either you have a fair coin and you got this unusual result by random chance, or you come to the conclusion that, this initial assumption that my coin is fair, that's wrong, and that's an easier explanation here. Okay, and so, getting only 5 heads out of 20 flips is quite extreme. We have a small tail over here, we have a small tail, so this would be 5 heads or fewer, and over here would be 15 heads or more. And these are pretty unusual, okay? We're expecting something around 10 heads, we're getting, 5. So that's, these are what our diagrams look like, okay? All of these diagrams, we've had a normal distribution here. And we can use the normal distribution because of the central limit theorem. The central limit theorem says, these sampling distributions that we're making, they're not exactly normal, but they can be approximated with the normal distribution. That using the normal distribution provides a good approximation. But in order for us to use the central limit theorem, one of the things is our sample size has to be large enough, okay? Our sample size has to be large enough. Our sample has to be selected randomly. And if we're sampling without replacement, we don't want to sample too much, okay? So, number one, what do we do if our sample size is not large, okay? If the sample size is not large, then your normal distribution is not going to be a good approximation, and the p-values that you calculate might not be reliable, especially if you're kind of on that border of rejecting or not rejecting, okay? And so there are other tests that we can use when the sample size is small, but we're not going to cover them in our class, but there are other tests that exist. You have not a kind of family of non-parametric tests and other sorts of tests that are out there. Okay, and the other issue is a little bit more critical in that if you don't have a random sample, we basically just can't use it at all, okay? If you don't have a random sample, we can't generalize the finding from the sample to the general population. In a lot of medical experiments, you can't get a random sample, right? You have to ask for volunteers to be participants in your study, and that's not going to be random. And so in those cases, researchers, they just have to kind of hope that their sample or their participants are representative of the population, okay? And maybe that's a reasonable assumption, a reasonable hope, and in other cases, maybe it's not, okay? But even if the sample isn't random, one thing that helps is, randomly assigning treatments can still be done, and you can still draw cause and effect conclusions if you do that, okay? And ideally, you would then be able to replicate the results of the study on a kind of another group. And so if it worked over here on this sample of patients, and then you got similar results over on this other group, then we can say, okay, well, we're hoping that this then generalizes to kind of the greater population. There are errors that are inherent to the hypothesis testing process, or just errors, I guess, really to statistical inference. These are not like you made a mistake in your calculation and we're going to take points off on your exam, okay? This is just, there is uncertainty, and because of the uncertainty, there are errors that are simply unavoidable, okay? Anytime you make a conclusion about the population based on a sample of data, there is always the possibility that you're going to make a mistake because of the random nature of your data, okay? So just by the very fact that you aren't observing the population directly and you're only looking at a sample means occasionally you're going to be led astray because your sample is selected randomly, kind of by random chance, you might get a sample that looks different from the population. You're making a conclusion based on your random sample, and you're going to come to a conclusion that your population is actually different, right, from what it actually is. And that's just because of the random nature of sampling. Every now and then, because of random sampling, you're going to get a random sample that looks nothing like the population, and you're going to make the wrong conclusion. And that's unavoidable. When you have a sample and it's a random sample, you don't know, is this a good sample or is this a bad sample? Okay? You don't know. When we set up the hypothesis test and we have kind of this alpha of 5%, the math is done in such a way that like 95% of the time, your random samples will lead to the right conclusion. But 5% of the time, again, just because it's a random sample and you don't know if your random sample is like a good sample or a bad sample, you're going to make the wrong conclusion. So there are two kinds of mistakes because there's two kinds of conclusions you can make, right? One conclusion is you reject the null hypothesis, and the other conclusion is you don't reject the null hypothesis, and you always run the risk that the conclusion you make is wrong. Unfortunately, when we were when statisticians were kind of studying this, they realized, yes, we can make mistakes, and there are two types of mistakes. And when they named them, they gave it the worst name possible that don't tell you anything about it. The mistakes there is like, oh, there's two types of mistakes, and we're going to call it the type 1 error, and we'll call it the type 2 error, which is completely not helpful, right? Later on, we came up with better names. We said the type 1 error, we'll call this the false positive, okay? And the type 2 error will be the false negative. Those are much better names. Those help us remember or understand what the mistake is. But unfortunately, the names type 1 error has kind of stuck around in the literature. Type 2 error has still stuck around in the literature, so you have to learn those as well. So the type 1 error is the false positive. This means we reject the null hypothesis. We sound the alarm, but in reality, the null hypothesis is actually true. We should not have rejected it. That's the false positive. The type 2 error is the false negative. We do not, our decision is not to reject the null hypothesis, but that's a mistake because in reality, the null hypothesis is false and it should have been rejected. So that's the type 2 error, that's the false negative. So let me talk a little bit more about the type 1 error. Oh, before I forget, let me give you your first view quiz answer. Today's first view quiz answer is the letter B. B as in bear. B is your first view quiz answer. Okay, so the false positive. This is our decision is we reject the null, but this is a mistake. Okay, and it's a mistake because the null hypothesis is actually true. We should not have rejected it. So, let's say, I don't know, you do your study, you calculate a p-value of 4%, and you say, okay, my p-value is 4%, it's less than my significance level alpha of 5%. So we say, okay, my p-value is less than alpha, it's considered small. If the null hypothesis were true, it says, my data is unlikely to happen, and so I'm going to conclude that my null hypothesis is wrong, and I'm going to reject it, right? So later on, it turns out the null hypothesis actually is true, and the data we observed was really just a random fluke, okay? So again, it'd be kind of like you have a fair coin, and you flip it 20 times, and it lands heads only 5 times out of 20. Okay? Could it happen by random chance? It could. And if it actually did happen, you might come to the conclusion, right? You did your study and you say, 5 times out of 20 is pretty rare, so I'm going to come to the conclusion that something's wrong with my coin. Okay? And in a lot of cases, that would be the right conclusion. But maybe in this particular case, you are wrong. It actually is a fair coin, and you actually were one of the really lucky or unlucky, however you want to look at it, unlucky people who only got 5 heads out of 20 flips, right? So your coin actually was fair, and just kind of by some random coincidence, you only got 5 heads out of 20. And so you thought the coin is, that somebody's cheating and that you're using a fake coin or a rigged coin, but it actually was a fair coin all along, okay? That would be a false positive. And so we would say, your decision to reject the null hypothesis when in reality it was correct is a type 1 error, a false positive. Okay, the type 2 error is just kind of the flip side. Okay, your conclusion is not to reject the null hypothesis, but in reality, the null hypothesis was false, and we should have rejected it. Okay, so let's say you do your calculations, right? You flip the coin 20 times, it lands heads, 6 times out of 20. Okay, maybe 6 times out of 20 isn't weird enough for you to come to the conclusion that this was a fake coin. Okay, so your p-value is 7%, your alpha is 5%, and you'd say, okay, well, my p-value is greater than alpha. I'm not going to reject the null hypothesis, and this is not weird enough for me to kind of question whether this is a question if this is a fair coin or not. I'd say, okay, it's possible that I just get this just by random chance. Okay, but later on, it turns out the null hypothesis actually was false, that this was indeed a trick coin. Okay, we should have tried it. We should have detected that. We should have figured it out that the coin was actually unfair, and that would be a type 2 error. We come to the conclusion not to reject the null hypothesis, but in reality, the null hypothesis was wrong. You often make a type 2 error if you don't collect enough data in the first place. Okay, so a lot of times, you collected maybe 40 observations, and really to make a good conclusion you needed 100 observations or something, right? So it often happens if you don't collect enough data. Okay, and it's also possible that by a random fluke you end up with misleading results. So for example, you could have a coin that's actually unfair, right? Maybe it's supposed to land heads only 30% of the time. But also by a random fluke, let's say you flip this coin 20 times and it lands heads 10 times out of 20. Okay, it's actually an unfair coin, but the unfair coin happens to give you results that look fair. Okay, and so you come to the conclusion, oh, there's nothing wrong with my coin. But in reality, it actually was an unfair coin. That could happen too, right? And there's really no way of knowing. There's no way of knowing what scenario are you in, right? We're always hoping that our random sample is representative of the population, but there's no real way of knowing. And we're kind of trusting that in random sampling, most of the time, the random sampling process does produce a sample that's representative of the population. And it will most of the time, but it's not guaranteed to do so. So here's kind of a little table. I don't know if this is helpful or not, but in truth, if the null hypothesis is true, then the correct decision will be not to reject the null. But if your decision is to reject the null, that's a type 1 error or a false positive. If the truth is that the null hypothesis is false, the correct decision is to reject the null hypothesis. That's what we want. If the null hypothesis is false, we want to reject it. And if we don't reject it, that's a type 2 error, or that's a false negative. We get to choose our significance level alpha. Significance level alpha is equal to the probability of committing a type 1 error. Okay, we get to choose it. So if we choose to use alpha equal to 5%, we're basically saying I am okay with the risk of making a type 1 error 5% of the time. I'm okay with making a false positive 5% of the time. That's what it means to choose a significance level of 5%. If you want to reduce the risk of making a false positive, you can choose to use a smaller alpha. You can say, you know what? I don't want to make a false positive, okay? And you can do that. You can just say, okay, well, I'm going to set alpha to be only 1%. Now, in order for me to reject the null hypothesis, my p-value has to be 1% or less. Fine, okay? You have now reduced your risk of making a false positive. You reduce the risk of type 1 error, okay? But the downside of that is now we've increased the risk of type 2 error, okay? Now we're saying, okay, before I reject the null hypothesis, I need stronger evidence. I need more extreme results, okay? If I flip the coin 20 times and it lands heads 5 times out of 20, that's not weird enough, okay? It's got to land only like 3 times out of 20, okay? At 3 heads out of 20 flips, then I'll be convinced that you have a trick coin. But if you're getting 5 heads out of 20, I'm not convinced. It could be a fair coin because a fair coin could get that result. I'm not, it's not convincing enough. I need something more unusual, something more extreme for me to come to the conclusion that my coin is a trick coin, okay? That's fine. That's your prerogative. But now you're going to be making a type 2 error more often. There's going to be fake coins, and they're not going to set off any flags because you've set this really high bar to kind of, for you to kind of reject it, right? You're setting this very high bar of what kind of extreme data you need before you reject the null hypothesis. So there's going to be kind of you're going to miss a lot of fake coins, right? You're going to, or whatever it is, right? So you need really strong evidence to convince you before you reject the null hypothesis, but now you're going to make a lot more type 2 errors. And, if you ever are in charge of a study, you get to choose what significance level to use. And whether you should pick a large alpha or a small alpha really depends on the situation and depends on what the consequences of a type 1 error and what the consequences of a type 2 error are. Which one's worse? That should guide whether you use a large alpha or a small alpha. Okay? Now, if no one says anything, then probably the default choice for alpha is 5%, right? If you're not sure what alpha to use, 5% is usually a good enough number in most scenarios. 5% is a totally arbitrary decision, though. There's no there's not like a scientific rule for why we choose 5%. I think we choose 5% probably because we have 5 fingers. It's something around there. 5% is kind of low enough, but not super small or something, and that's just kind of the number that we've accepted and has kind of persisted, and we use 5%. But, it is an arbitrary choice. If somebody says, hey, why are you using 5%? It's a little bit of an arbitrary choice. It's kind of like, why is, age of adulthood 18? Okay? Is there, when you turn 18, now you can vote and you can take out, open bank accounts and take out loans, and you can, join the military and stuff. But then we say you can't drink until you're 21, or, these are just kind of arbitrary numbers that, something around 18 probably makes sense, but, some people are more mature at an earlier age, and some people take longer to, reach, maturity and things like that. 18 is probably reasonable for most people, and it's kind of an arbitrary number, but that's what it is. And 5% is a bit of an arbitrary number. It's probably good enough for most circumstances, though. Okay. So anyway, here I wanted to kind of present a couple scenarios where we ask, what is a type 1 error? What's a type 2 error? Which is worse, a type 1 or a type 2 error? Okay. So the scenario is a patient visits a doctor for a disease screening. Okay, patient visits a doctor for disease screening. And generally we assume patients are healthy unless they show symptoms of illness. So our null hypothesis is that the patient is healthy. The alternative is the patient is sick. Okay? And ideally what we want, ideally is if you're healthy, you get cleared, you get sent home. The doctor looks at you and says, oh, you're fine, go home. Okay? And then if you're sick, you receive medical attention. That's what we want. Everyone who's healthy gets sent home. Everyone who's sick gets medical attention. Okay, what's a type 1 error and what's a type 2 error? What's the type 1 error in this case? Anybody? Yeah. Oh, go, either of you.
I think the one error is that everyone who's healthy gets cleared. No, wait. The one who is healthy gets medical attention.
Yeah, so a type 1 error is would be the false positive. Somebody who's actually healthy is said, oh, you're sick. You've got an illness. Okay, you should stay home in quarantine or something. Okay, and then a false negative would be somebody who is actually sick, gets cleared and sent home. Right. So what would you say is worse? Yeah. Yeah, probably the sick person getting sent home is probably worse here, right? So if you think of like early days in the pandemic, we said the type 2 error is really bad, okay? And so we operated with a very large alpha. We said, oh, if you have a cough, just stay home. Don't leave your house, okay? If you cough, don't go outside, stay away from other people, quarantine, something like that, okay? And we really wanted to kind of minimize false negatives, type 2 error, right? Because we really didn't want a sick person to go out and start infecting other people and things like that. We said the type 2 error is worse than the type 1 error. We should pick a large alpha, okay? There's like websites, like WebMD. I don't know if you've ever gone to WebMD and you typed in some symptoms, okay? And, the joke is anytime you go to WebMD and you type in your symptoms, it's going to be like, you have cancer, you got to go see the doctor. It's possibly life-threatening, okay? And that's, WebMD is just operating with a large alpha. They are kind of operating under the assumption that if somebody types in their symptoms, it is much worse to tell the person they're fine and nothing's wrong with them when they actually do have a disease like cancer or something, okay, versus sending them to the doctor where the doctor can do further tests and decide, whether this person actually needs medical attention or not, okay? So that's what we have. Now, as the consequences of a false positive get worse, okay? So it's telling somebody to stay home. If it's a false positive and we say stay home, the consequences of that aren't that big of a deal, right? Somebody just has to stay home. It's not a huge loss, okay? But if the consequences of a false positive get worse and worse, for example, chemotherapy as a treatment for cancer, chemotherapy is, this very, very harsh series of chemicals and stuff that, they kill cancer cells, but they also take a very heavy toll on the human body. And so it would be a kind of a very bad mistake if a patient is given chemotherapy, but they never actually needed it. If they never actually had cancer and they were given chemotherapy, that would be a very bad mistake. So in that case, because the consequences of a false positive are much worse, you operate with a much lower alpha, and it takes a lot of evidence, right? So you're going to go through a series of tests. You get biopsies and all kinds of different tests, and the doctors have to really be sure that you do have cancer and that this is the best treatment in this scenario before they start you on on these medications. Okay, and so because of that case, in those cases, if the false positive is worse, you operate with a lower alpha. So you think about what's the consequence of a false positive? Consequence of the false positive is you stay home from work. Okay, not that big of a deal, right? Just sure. If you have any symptoms of illness, we say, hey, stay home, don't come to school, make up your work later, okay? But if the consequences of a false positive are like, we're gonna cut you open, all right, for surgery, okay? They're not gonna, you don't go to the doctor and you say, I've got a cough, and they go, oh, okay, let's put you on the surgery table. You get a whole bunch of exams, x-rays, CAT scans, all kinds of things, biopsies, to kind of make sure this is the right procedure, right thing to do. All right, here's another scenario. Imagine a criminal trial, right? So in the United States, we assume defendants are innocent until proven guilty. So our null hypothesis is that the defendant is innocent, and the alternative is the defendant is guilty. And what we want, the ideal scenario, is if you're innocent, you're acquitted. Everyone who's innocent is acquitted. Everyone who is guilty is convicted. That's what we want. We want guilty people to, receive justice, okay? And we want innocent people to be let go. A type 1 error is a false positive. This would be an innocent person is convicted. Innocent person goes to prison for a crime they never committed. And a type 2 error is the false negative. A guilty person is let go. A guilty person committed a crime, but doesn't have to face any penalty for it. Okay. Now we want to avoid both of these things. Both of these things we want to avoid. If we had to, and this is always up for debate, but if we had to kind of design a society and prefer one type of mistake over the other, okay, our justice system is set up in such a way that says the type 1 error, convicting an innocent person, is worse than letting a guilty person go free, okay? And so we say the type 1 error is worse than the type 2 error, and so we should pick a small alpha, okay? We want to reduce the risk of type 1 error. We operate with a small alpha. And they say this in trials. It's not, they don't specifically say use a small alpha, but they use the phrase beyond a reasonable doubt, okay? Before a jury reaches a conviction, comes to the conclusion of guilty, they say it must be beyond a reasonable doubt, all right? They don't want the jury to convict based on some kind of hunch or just kind of strange feeling. They want the jury to, be convinced beyond a reasonable doubt before they reach a guilty verdict. It is not possible to have alpha equal to 0. Okay, so you can imagine, in some cases, maybe one judge will determine guilty or not guilty. All right, and it could later turn out, let's say a judge convicts someone, sends this person to prison, and later on, evidence comes forth that exonerates the defendant, right? And the judge feels guilty, right? Because sometimes we hear these stories about people who are convicted of crimes they never committed. They're freed from prison, after spending 25, 30 years in prison for a crime they never committed, and we feel such I don't know what the right word is, but we feel like that was a terrible injustice that happened to this person. And it's possible that maybe one day a judge receives news that someone they convicted was actually innocent, and the judge feels very guilty about this and says, I never want this to happen again. I want to completely avoid a type 1 error. Well, the only way the judge can be absolutely sure never to commit a type 1 error, okay, never to falsely convict someone, is to never convict anyone. Because as soon as the judge convicts someone, there's always the risk that this person was innocent, and that the amount of evidence that was presented, that there was just some weird, strange confluence of coincidences that resulted in this evidence that looked very convincing, but again, maybe could have been explained away. So it is impossible to completely avoid type 1 error. And so, we have to operate with, I guess, an acceptable amount of type 1 error. But yeah, we do want to avoid it. So we operate with a low alpha, but it's not possible to have alpha equal to 0. All right. Any questions, or does that all kind of make sense here regarding type 1 and type 2 error? All right, here's a little bit of, I guess, stats humor. So here it says, our null hypothesis will be the patient is not pregnant. And here is the false positive, the type 1 error, where the doctor is telling this man that you are pregnant when clearly he is not. And the type 2 error would be the doctor telling this woman who is clearly pregnant, or at least what this illustration is supposed to depict, and the doctor saying you're not pregnant, okay? Medically speaking, probably a type 2 error is worse than a type 1 error, but in a conversation with a friend, making a type 1 error, it would be considered to be a very bad mistake. And so, again, the only way to fully avoid type 1 error is to never make this statement, never reject the null hypothesis. So never ask somebody if they are pregnant. We have some one-sided and two-sided alternative situations when we come up with our alternative hypotheses. And whether we use a one-sided or two-sided alternative is based on how the question is worded or written. Okay? So if you have a sentence and the problem asks, do we have data? Do the data provide evidence that the proportion is, say, greater, or the proportion is more, or something along those lines? Your one-sided alternative will have a greater than sign. Okay? And in that case, the p-value will be equal to the area to the right of whatever test statistic you find. Okay? Sometimes your questions will say, hey, do we have evidence that the proportion in the population is less than, or lower, or smaller, or some other kind of word like that? And in that case, your alternative hypothesis has a less than sign. And your p-value is equal to the area to the left of the test statistic. And then sometimes you'll just have questions like, hey, do we have evidence that it is different, or it has changed, or is no longer the same? Okay? And, those words don't suggest did it get higher or lower or anything like that. Just, is it different now? Okay? In those cases, we have a two-sided alternative. The p-value will be equal to double the tail area. So you say, okay, how much area is beyond the test statistic? So if your z-score is negative, beyond is z or more negative. Or if it's positive, it's z or more positive, so to the right. So double the area to the left of negative z, or double the area to the right of positive z. This is all text on this slide. Maybe a couple diagrams would make a little bit more sense, or some examples here. Okay, before I get on to this slide, let me go ahead and give you your second view quiz answer for today. Second view quiz answer today is the letter E. E as in elephant is our second view quiz answer. E. Okay. So in some scenarios, it is possible you end up with the wrong p-value, or I'm sorry, the wrong direction on the alternative hypothesis. Okay. So, for example, let's say we're revisiting kind of this census and the seniors proportion example. All right. So we said last census, the proportion of seniors was 22%. And we say, okay, do we have evidence that the proportion of seniors is going up, right? Is our population getting older, right? Are people having fewer children and things like that? And, in some countries like Japan, they're facing this situation where the population just gets older and, fewer people are having children. And so we want to know, is that a problem that we're witnessing here, okay? So, they go out and they collect a random sample of people, of citizens, random sample of 200 people, 40 of them are seniors, okay? So in this case, because of the way the question is phrased, we're seeing if there's evidence that the proportion of seniors has increased since the last census. Our null and alternative hypothesis will be, well, null always has an equal sign, that p is still equal to 0.22. The alternative is going to be that p is greater than 0.22. That's going to be the alternative. Okay. What do our data show, though? Okay. When we look at our data, we do 40 divided by 200. In our data, we only have 20%. Only 20% are seniors. Okay. So at this point, there's not even, we don't even have to carry on with the test, okay? Because someone says, hey, do we have evidence that the proportion of seniors is going up? Well, I just took a sample of 200 people, and only 20% are seniors. So if anything, it looks like the proportion of seniors is actually going down, okay? Because last time it was 22%, and when I took a random sample, it's only 20%. So it appears, if anything, that the proportion of seniors is a little bit lower. Now you can say, well, go out and collect more data. Sure, we could do that. But based on the data I have right now, it doesn't look like the proportion of seniors is increasing. If anything, it might look like the proportion of seniors has decreased. Okay, so in that case, we don't even have to continue. We could just say, well, my data is going in the opposite direction of the alternative. So whatever my p-value is, it's going to be over 1/2. Now, I could go through the math, and we could try to find the proportion, okay? So if I did this, if I carry out the test, okay? So remember the null hypothesis is that p is equal to 0.22. The alternative is that p is now somehow greater than 0.22, okay? The greater than sign means the p-value is the area to the right of our test statistic. Right? So my p hat was 40 out of 200. My p hat is 0.2. Okay, so when I do this, if the null hypothesis were true, I would expect 22%, and what I actually got was 20%. And the p-value says we're going to take the area to the right. So we can see from this diagram my p-value, whatever it is over 1/2. So my z-score is p hat minus the p in the null hypothesis divided by our standard error. Standard error is square root of p0, 1 minus p0, and 0.22, 0.78 divided by 200. .02929. Okay, get negative 0.68. All right, so I get this is equal to z equal to negative 0.68. So the area to the right of that this area is equal to 0.7517. 0.7517. And I think, yeah, that's what I have written here. That's my p-value. I would say do not reject the null hypothesis. But again, you know, it wasn't even necessary to kind of go through this because, again, my data ended up only 20% seniors. And we were asking, hey, do we have evidence that it's now higher than 22%? And we'd say, yeah, no, we don't have evidence that it's higher than 22%. Okay? Okay, a lot of times, in a lot of other cases though, when you use a two-sided alternative, your p-value a lot of times ends up being double the one-sided alternative, okay? If you don't have this, so I mean this scenario could happen where the one-sided alternative ends up being over 0.5, that could happen. But in most scenarios, your one-sided alternative is just like, you know, is like this correct side, you know, the smaller side of the tail, and then your alternative hypothesis, if it's non-directional or if it's two-sided, will be double the one-sided. Okay, and so some people look at that and they say, oh, you know what? My p-value when it was two-sided or non-directional, my p-value was like 6%. But if I cut it down to a one-sided alternative, it'll only be 3%, okay? And if my significance level is 5%, you know, at 6% I wouldn't reject the null, but if I cut it in half and I get 3%, now I will reject the null, okay? That decision of whether you use a one-sided or two-sided alternative should be done before you look at the data. And it's kind of considered cheating if you just try out a whole bunch of different hypotheses and you say, well, maybe I'll cut the use a, greater than sign or a less than sign in order to kind of shape my hypotheses after the data, after I look at it, okay? And that would be kind of considered cheating. And the answer is, the truth is, okay, so let me back up for a second. So one thing that always irks me a little bit is when people say something like, oh, you know, with statistics, you can say whatever you want, right? And there's kind of this, like an implication that you can be dishonest with statistics. And I would say it's not statistics that's dishonest, it's people, right? People can be dishonest. And if somebody wants to try to take things and mislead you, they can do that. But from an ethical standpoint, you should come up with a hypothesis and then test your hypotheses against the data, and not the other way around. If you start off with the data, okay, you can almost slice your data in some kind of weird way where you end up with a small p-value and you end up rejecting the null hypothesis, okay? Anytime you have a big set of data, you can almost slice it in some kind of way where you say, oh, you know, look at this weird thing that we saw in the data, and what's the probability of this happening by random chance? It's really small, and therefore we're going to come to this conclusion, okay? But chances are you just highlighted just some kind of weird oddity that just was coincidental as far as your data goes, all right? There's a comic that kind of captures this idea. It's from this web comic called XKCD that I highly recommend. And it starts off like this, okay? This person runs in and says, jelly beans cause acne, and the partner says, scientists investigate. And the scientists return and say, we found no link between jelly beans and acne. The p-value is greater than 5%. And they say, okay, well, that settles that. And then the person objects and says, I hear it's only a certain color that causes it. Only a certain color that causes acne. Okay, scientists. And then so they come back and they do a bunch of tests. And they said, we found no link between purple jelly beans and acne, p greater than 0.05. We found no link between brown jelly beans and acne, p greater than 0.05. We found no link between pink jelly beans and acne, p greater than 0.05. No link between blue jelly beans and acne, p greater than 0.05. No link between teal jelly beans and acne, p greater than 0.05, okay? And it keeps going. No link between salmon jelly beans and acne, no link between red jelly beans and acne, no link between turquoise jelly beans and acne, no link between magenta jelly beans and acne, no link between yellow jelly beans and acne. All of those have p-values greater than 0.05. Okay, we found no link between gray jelly beans and acne, no link between tan jelly beans and acne, no link between cyan jelly beans and acne. All of those have p greater than 0.5. Okay, we found a link between green jelly beans and acne, p less than 0.05. Okay, and then and they keep going. We found no link between mauve jelly beans and acne, no link between beige jelly beans and acne, no link between lilac jelly beans and acne, no link between black jelly beans and acne, no link between peach jelly beans and acne, no link between orange jelly beans and acne. All of those have p-values greater than 0.05. Okay, and of course, what gets published? News: green jelly beans linked to acne. 95% confidence, only 5% chance of coincidence. Scientists and so on and so forth. Okay, and I think this setup illustrates the issue with this, is that they've sliced the data in so many ways that almost, they were almost certain to end up with some kind of weird set of data where it appears that there's a link between, this particular color of jelly beans and acne. And sure, what's the probability of getting this by random chance? The probability of getting this result by random chance is less than 5%. But if you think about it, they did like 20 of these different tests, okay? And the probability of committing a type 1 error for any one of these tests is 5%. And, if you do 20 of these things with a 5% risk, you're almost expected to make a type 1 error at least one time somewhere along the way. And that could happen, right? If you keep changing your hypotheses, just kind of searching and hoping to find something unusual in the data, you'll probably find something. But that's not the way we do scientific research, right? We start off with a question, we go out and gather data, and then we see, does this data either, support or reject? Does this data, help me reject the null hypothesis? Okay, and if the answer is no, it doesn't. We don't just say, oh, well, I spent a lot of effort gathering this data. Can I slice it in some other way where I find something interesting? Because almost certainly you can, but it's not necessarily something that's going on there. As statisticians, we never use the word prove. Okay, so statisticians will almost never say that the data prove some sort of conclusion. We might, at best, we'll say we reject the null hypothesis, and we say we have evidence that supports the alternative. Okay, we have evidence that this medication is effective. Okay, we reject the null hypothesis would be that it's not effective, that it's the same as doing nothing. And if we reject that, we have evidence that the medication is effective. Okay. On the other hand, if we do not reject the hypothesis, and this is frustrating, but we can't say we have evidence that the medication is ineffective. All right. All we can say is, okay, the null hypothesis was that the medication is no different than doing nothing, and we didn't reject it. And so we say, right now we have no evidence that the medication is effective. Okay. But saying I don't have evidence that the medication is effective is not saying the same thing as I have evidence that the medication is ineffective. Right? Lack of evidence for something is not necessarily the same thing as evidence that it doesn't exist. Okay? So, and that's often a frustrating thing, because sometimes we want to say, here's the conclusion, it doesn't work. Okay? All right? All we can say is, I don't have evidence that it does work, which can be frustrating. Sometimes we want to say, I have evidence that it doesn't work, but we can't say that. All we can say is we don't have any evidence that it does work. there's also another thing to think about when making conclusions, and it's this idea of statistical significance versus practical significance. Okay, we say things are statistically significant when we reject the null hypothesis. Okay, and if we reject the null hypothesis, what that means is that our data that we have is unlikely to happen by random chance alone if the null hypothesis were true. So, you reject the null. The coin has landed heads only 3 times out of 20 flips. And we say, you know what, this is unlikely to happen if it were a fair coin. Therefore, I come to the conclusion that the reason why I got 3 heads out of 20 flips is because my coin isn't fair. Okay? But statistical significance does not actually mean this is practically significant. Okay? Practical significant means that the result is actually useful or meaningful, and this can be only assessed by someone with knowledge of what is important or what is useful. Okay? So the example I have here is, you could be, a farmer. Maybe somebody comes and says, hey, you should switch over to, this new fertilizer system, okay? Or this new farming system. And if you switch over, it's going to reduce the amount of kind of bad produce, right? So, a lot of produce that gets produced on the farm never make it to market because it ends up a little bit ugly, right? People don't like to buy ugly tomatoes or ugly vegetables. They only like really pristine looking things, and so a lot of produce just doesn't make it to the market. And so they might say, oh, you know what? If you invest in this new system, you're going to reduce the amount of unsellable produce. Okay, great. All right. And the farmer says, okay, well, how much does this new system cost? Oh, it's going to cost, $2 million of new equipment and stuff. So that's a lot of money. He said, don't worry, you'll make it back, right? If you reduce the amount of unsellable produce, you'll make more money. You'll make this money back. So the farmer sits down with an accountant and financial planner and all of this stuff, and they say, okay, for it to be worth this investment, the unsellable produce has to go down from 8% down to 5%, okay? And if it does that, then sure, we'll make our money back in this amount of time. But if it doesn't, if it only goes from 8% to 7% or 8% to 6%, then yeah, you know what? You'll reduce your unsellable produce, but you're not going to make your money back. It's not going to be enough of a reduction, right? And so, maybe we do kind of a test run and see what happens, and it reduces the unsellable produce from 8% to 6%, and it's a statistically significant result. This is not the result of just random coincidence, but actually does show that this new farming system is effective. We are reducing it, in fact, from 8% down to 6%, okay? However, the financial analysis says, this is still not big enough of a difference for it to be worth it, right? So that could happen, right? Should you buy a hybrid car versus, conventional gas? I mean, this decision will be taken away from us in a few, I guess, a decade or so. But sometimes if you can do some kind of calculation and say, all right, well, how much money will I save if I go hybrid versus fully electric or just gas only? Okay, versus how much more does this car cost to do? And in the beginning of when electric cars were first coming around, electric cars were significantly more expensive, and that you would have had to do X amount of driving in order to kind of recoup that cost in gas savings. So if money saving was the only motivation, it might not have been the right choice for a lot of people. Okay, there's certainly other benefits other than money saving on gas, but it's better for the environment and stuff like that. But but these are things that, people have to consider and think about, and just, it's not, the answer of is it statistically significant or not may not actually be the same answer as is it practically significant. And this answer of practical significance requires an expert who knows, at what point is this difference actually important. So statistics is only able to tell us that this difference from 8% to 6% is unlikely to happen just by random chance, but whether it's actually a good investment or not requires, specific knowledge of that kind of subject. Okay, so that wraps up kind of the conceptual deep dive. Let me get into now we'll introduce kind of another hypothesis test, still in the same chapter. We're now looking at proportions, but we're comparing two proportions, okay? And so back in, one of our earlier chapters, I think chapter 5, we asked kind of this question of, are two events independent, okay? And we said if they're independent, the probability of A given B is the same as the probability of A given not B. And, we kind of just left off and said if they're the same, they're independent, and if they're not the same, they're not independent. And, we said, hey, I think the example we used was, is the proportion of truck owners from California, is that the same as the proportion of truck owners in Texas, right? In Texas, what proportion of people drive pickup trucks versus California? And we said, okay, well, these proportions are different. Therefore, these events are not independent, okay? And then I think the other example we used was, is being left-handed and wearing glasses, are those independent or not? And, the example that I gave was that, okay, the proportion of glasses wearers who are left-handed is the same as the proportion of people who don't wear glasses who are left-handed, right? So I think we said 10% of glasses wearers are left-handed and 10% of non-glasses wearers are also left-handed. 10%, 10%, those are the same, so they're independent, okay? And so this is the old slide. We said proportion of truck drivers from Texas is 36%. Proportion of truck drivers from, California is 30%. They're different, not independent. Over here, we said proportion of left-handed people is 10% if you wear glasses. Proportion of left-handed people if you don't wear glasses is 10%. They're the same, therefore they're independent. What we never factored in was randomness, okay? What if being left-handed and glasses is independent, but just by random chance, we ended up with one more person who's left-handed and wears glasses, right? We ended up with 7 people here, okay? Well, that would throw this off, and we would come to the conclusion that they're not left-handed if we just kind of use this old thing, right? So what we're going to learn now is hypothesis testing, and we're going to say, well, can we account for this randomness? Okay, if one sample has this proportion and another sample has a different proportion, okay, maybe these two proportions aren't exactly the same, but is it possible that the populations have the same proportion? That's what we want to test, okay? Is it possible for two populations to have the same proportion even if their random samples have slightly different proportions, okay? If one random sample is 10% left-handed and another random sample is 12% left-handed, is it possible that the respective populations, okay, is still the same, all right? And so that's what this test is all about. The two proportion z-test is a hypothesis test to see if two populations could have the same proportion, or if there's evidence that those two populations have different proportions. Okay, so how do we do this? So here's an example. All right, so this one is, does my lucky charm work? Okay, so I don't know if you're 21 or not, if you can go to Vegas and gamble. You shouldn't, okay? Law of large numbers says that in the long run, the casino's gonna make money off of you, okay? But I will admit it is still sometimes fun to play a game, okay? But I'm not recommending that, okay? So let's say you have a lucky charm, all right? Or you think something that has a lucky charm, all right? And you decide to play, and you're gonna do a statistical test, right? So you say, okay, when I carry my lucky charm and I went and I played 50 different games, right? I don't know, you played the slot machine 50 times or something. You won 26 times and you lost 24 times, okay? So you won 52% of your games when you had the lucky charm, okay? When you didn't have the lucky charm, you played 50 games without the lucky charm, you won 20 times and you lost 30 times. So you only won 40% of the games, okay? And so you might say, look, with the lucky charm, I won 52% of the time. Without the lucky charm, I won only 40% of the time. Therefore, my lucky charm works. I'm going to stick with it, okay? Or is it possible that this difference is just from randomness? Is it possible that the lucky charm actually doesn't really do anything, but just by random coincidence, we happen to get 26% or 52% versus 40%? That's the question that we want to know, okay? Even though I got 52% and 40%, and that's different, is it possible that with or without the lucky charm doesn't really matter? This was just a random coincidence. This is what we want to ask. All right, so how do we do this, okay? Well, it's important to kind of just define symbols. And so we have two proportions that we want to know. One is the proportion of wins with the lucky charm, and the other is the proportion of wins without the lucky charm. So I'm going to call with the lucky charm P1, and the proportion of wins without the lucky charm P2. Okay, and we want to know, could P1 and P2, the proportion of wins with or without the lucky charm, could they be the same number? Okay, or do I have evidence that my lucky charm works, that P1 is a higher number than P2? So these are going to be my hypotheses. Okay. I kind of want to pause there and just make sure this is okay. P1 equal to P2 is our null hypothesis, and our alternative, this one is directional, a one-sided test, because I want to know, does my lucky charm work? Am I luckier with the lucky charm? Is P1 higher than P2? Okay, and so far our data looks like maybe it could be, right? Because in my data I won 52% versus 40%. So it looks like maybe it could be. All right, well let's try it out, right? Oh, okay. So here we check the conditions. The conditions are, we need to have at least 10 successes and 10 failures, and so large samples, and I played 50 games, 26 and 24 versus 20 and 30. All of those numbers are greater than 10, so we're good. Okay. Random samples, we're playing casino games, so these are random. Okay. Our samples are, our observations are independent and things like that. So all of these conditions are met. I'm gonna just kind of skim over this, and if you want to read this in more detail, you can. All right. So what we have to do is we have to figure out, okay, what are our sample data? So first, the observed proportion that we got with the lucky charm is 26 over 50. I won 52%. The observed proportion without the lucky charm, so this is P2 hat. So I have P hat 1, I guess P hat 1 and P hat 2. P hat 1 is 52%, P hat 2 is 40%. So this is what I observed in my data, okay? These are new formulas here. The overall proportion of success. This is in total, what is the proportion I won? So whether or not I had the lucky charm, how many games did I play total, and what percentage did I win in total? That's your overall P hat, So you say, okay, well, how many games did I win total? I won 26 plus 20. I won a total of 46 games. How many games did I play total? You do 50 and 50. I played a total of 100 games. So my overall P hat is 0.46. Okay, so the overall proportion of success. And you don't need to have the same n size. Here I have 50 games with the lucky charm and 50 without. It's okay if they're not. You know, you could have played 60 games with and 40 without or something. You just take the total number of games you played, or the total n, that's your denominator, and the total number of successes or total yeses in your numerator, your overall proportion of success. And once you have that, you have to find your standard error. Your standard error is just this ugly formula. There's nothing we can really do about that. This is just the standard error formula that we have. So you find your overall proportion of success, p hat times 1 minus p hat, and we have two n's, two samples, so times 1 over n1 plus 1 over n2. So, you know, just star this page in your notes so that you can find these formulas later when you need to do them, okay? So this is your standard error, and if you go through the calculations, you get a standard error of 0.0997. So pretty much 0.1, but 0.0997, okay? Standard error of around 10%. Okay, what is our test statistic? We're going to take the difference between what I observed, my two proportions that I observed. So with the lucky charm, I won 52%. Without the lucky charm, I won 40%. So that's a difference of what? 12 percentage points, difference of 0.12. 0.52 minus 0.4 gives me 0.12. I divide by my standard error, which is, you know, practically 0.1. So I get a z-score of 1.2. Z-score of 1.2. So again, just kind of the idea here being, right, so my null hypothesis is P1 is equal to P2, all right? And what I got was P hat 1 was 0.52, and P hat 2 is equal to 0.40, okay? So if the null hypothesis were true, okay, we expect P hat 1 minus P hat 2 to be around 0. This is what we would expect, okay? And so my standard normal distribution, it would be centered at 0. What I observed, okay, we observed P hat 1 minus P hat 2 to be 12 percentage points, 0.12, okay? 0.52 minus 0.4, okay? And we want to, okay, what's the probability that we get this or something more unusual, right? So the z-scores, this turns out to be equal to a z-score of 1.2, right? Because my standard error over n1 minus 1 over n2. We get 0.997. No, 0.0997. So we get 0.52 minus 0.40 divided by 0.0997. We get z equal to 1.2. And the area to the right of 1.2 is the area to the left of negative 1.2. Oops. Can't I? So negative 1.2, 1.1151. This is the number we're going for. All right, so our p-value is 0.1151. Okay. So, yeah, this difference, it feels like, oh, that's a significant difference. I won 52% versus only 40%. But it turns out that even if the lucky charm did nothing, we could get results like this with a probability of around 11, 12%, okay? So it's not convincing, right? I mean, it could be that the lucky charm actually does work. Like when I'm carrying the lucky charm, maybe it has some kind of psychological effect and I make better choices in blackjack or something. Who knows, okay? There could be an effect, but it's also possible that it's not, there's no effect, and we just got these results just by random coincidence too, okay? Or there could be some, supernatural forces with the lucky charm. We're not saying anything, yes or no. We're just saying, okay, you know what? My p-value is 11.1151. It's a little bit higher. It's higher than 5%, so we're not going to reject the null hypothesis. And, despite winning 52% versus 40%, this difference of 12 percentage points, it's not statistically significant. Okay, it could have been the result of random chance. It could have been the result of random coincidence. And so we cannot come to the conclusion that the lucky charm actually increases the probability of winning at the casino. Okay? Maybe it does, but the data we have is not convincing to us. All right, let me give you your last view quiz answer. Last view quiz answer today is the letter B. B as in bear. B. That is your last view quiz answer. Okay, we'll go ahead and we'll wrap it up here today. And have a good rest of your day. We'll see you guys on Wednesday. And that will be all. Okay, see you later.